Welcome. In this video, we're going to be talking through problems 2, 3, and 4 on the kinetics integrated rate laws practice set. So there's some examples of how we would use integrated rate laws. So let's scroll down and look at problem number 2. So we've got a problem saying we've got the decomposition of acetaldehyde to methane as a first order reaction. If the rate constant, so I'm going to start writing down things that are given. So it gives us the rate constant. K is 0.029 minutes negative 1. I might write this as 1 over minutes. How long does it take? So let's identify what the question's asking me for. It's asking me for time. For a concentration of 0.050 mole per liter minus 1. So that is my initial molarity is 0.050 molarity to reduce to a concentration of this. So that's my molarity after a certain amount of time has passed. So I've got a K, I've got initial molarity, I've got a final molarity, and I have a time. And the key thing with any type of calculation is there's two types of rate laws that you can use. Let's scroll back and look at this table on the top. Whoops. Let me navigate up here. So you've got the rate law, which is over here on the left, and you've got the integrated rate law, which is on the right. And you can use the rate law if you're given molarity and rate data, and you want to use the integrated rate law if you're given molarity and time data. So just look out for time. If you're ever asked about time or given time data, you probably want to use the integrated rate law. If you're given rate data, which is usually in some molarity per unit of time, you might want to be using the rate law. So this problem is asking me for time. So I'm going to use the integrated rate law. And we know we want to use integrated rate law. We have to say, okay, what order is the reaction? Well, it's a first order reaction. So I'm going to look on my equation sheet. Remember, you don't have to memorize the integrated rate laws. They're given on your equation sheet. And for a first order reaction, the integrated rate law is this: the natural log of my concentration at time t minus the natural log of my initial concentration equals negative kt. When you're doing these calculations, you have to be really careful with your negatives, because you got lots of, subtracting negatives of negatives. It can get really confusing. So just be careful with that. So we've got the natural log of 0.050 minus the natural log of, whoops, I put it in the wrong order. Okay, a sub t is 0.040, so this should be 0.040 minus the natural log of 0.050. Those are little things you want to be careful about. Equals negative 0.0291 over minutes times t. The natural log of 0.040 is negative 3.22 minus the natural log of 0.050 is negative 2.996. And then you're going to divide it by negative 0.029, and this is 1 over minutes. The natural log of a number is unitless, so I'm not going to write a unit on the top. So if you think about what the units of our answers are, it's going to be 1 over minutes. That just means minutes. And if you plug this in your calculator, you should end up with 7.7 minutes. I did it to 2 sig figs because my rate constant just had 2 sig figs in it. So there you go. Just be careful with negatives, and sometimes I find it helpful to actually stop and write the numbers out like I did right here. Sometimes when we do all the steps in our calculator, if we're not careful with parentheses, we can make mistakes. So do what you need to do in order to be kind of methodical with your work here. All right, let's look down at number 3. We've got a decomposition that is a second order reaction. That's probably an important piece of information. They give us a rate constant. So it's always a good thing to kind of write down what you're given in a problem. Okay, so it's k equals 0.080, and let's try and interpret this unit here. So a liters per mole seconds. So this is liters over molarity seconds, which is the same as 1 over, so it's the inverse of moles per liter, which is 1 over molarity second. So that's what that unit means. It's 1 over molarity second. That's the value of K. How long does it take? So we're solving for time again. For an initial concentration, so my initial molarity is 0.05. how long does it take for it to decrease to half this concentration? So my final molarity is going to be 1/2 of 0.05, which is 0.025. And again, I want to ask myself, what should I use? Should I use my rate law or my integrated rate law? The key thing here is if we're being asked for time, or if we're given time data, we're going to need to use the integrated rate law. Since it's second order, I want to use the second rate law, integrated rate law, shown on my equation sheets, and that's this one right here, 1 over a sub t minus 1 over a sub 0 equals kt. So I'm going to start plugging numbers in. A sub t is 0.025, and that's units of molarity. Don't forget units. That's 0.05 molarity. This is 0.080, 1 over molarity second, and then time. And if you plug this in your calculator, 1 over 0.025, that is 40. 1 over 0.05 is 20. The units of this number are 1 over molarity. And then you're going to divide that by 0.080, 1 over molarity seconds. Notice how 1 over molarity cancels out. You're left with 1 over seconds. So my answer is just in seconds. And how many seconds? It's 250. So that's how I use a second order integrated rate law. And now let's take a look at problem number 4, which I got some questions on. So we've got a reaction here, we've got some data, we can figure out the reaction order. So with respect to, let's figure out the reaction orders for X and Y, my two reactants. So it looks as though Y, if you compare like the first and second data set, when X stays the same and Y doubles, the rate doubles. So it looks like Y is first order. Now let's look at X. When you compare the first and third, and when you double the molarity of X, it looks like the rate stays the same. So the concentration of X does not affect the reaction rate. That means X is 0th order. So the rate law is going to be rate equals K times Y. All right, so now let's determine the value of the rate constant K. So again, I've got two options. I can use my rate law, or since I know it's first order, I can also use my integrated rate law, which would be the natural log of y times t minus the natural log of y times 0 equals negative k times t. You got to ask yourself, what info am I given? And in this case, I think you could actually use either option here. So, no, actually, I don't have any time data. So you have to actually use this first one right here. Because what we know is we know rate data and we know molarity data. So we can't actually use the integrated rate law. We're just going to use the regular rate law because we're given rate and molarity data. So let's go plug that in. It shouldn't matter which data set we use, either the first, second, or third should all give us the same number because, K is a constant. I'm going to plug in data from the first reaction set. So the rate is 7.0 times 10 to the negative fourth, molarity per second equals K. The concentration of Y is 0.10 molar. So if you rearrange this and solve for K, you end up with 7 times 10 to the negative 4 molarity per second divided by 0.10 molarity. Notice how molarities cancel out. What we're left with is 7 times 10 to the negative 3, 1 over second. Another way of writing this in standard notation is 0.007. You can also write the unit as S minus 1. So in this case, we found the rate constant using rate law because we had rate and molarity data. Okay. Remember, the rate constant K always has units, so always ask yourself, what are the units of K? So now let's look at D, and if you start with initial concentrations of this, how long must the reaction proceed? I'm going to start writing down what we know, because there's a lot of information here. So we know that X sub O is 0.8 molar. We know that Y starts at 0.6. We know that Z starts at 0. We're trying to solve for time, so I probably want to use the integrated rate law because I'm trying to solve for time. And how long must proceed to produce a concentration where Z, so Z at time t is equal to 0.2 molar. All right, so a couple of things here. Let's take a look at this integrated rate law. See if I can zoom in here so you can see it. It's right up here. And notice my integrated rate law is given in terms of y. So, and I also want to say is I know the value of k from the previous problem. So I know k equals 0.007 s minus 1. So I know the value of k. I'm trying to solve for t. I know the value of y sub 0 is given, but right now I don't know what y sub t is. So I need to know y sub t in order to use this equation right here. And I'm only given z at time t. Okay, but this equation is only valid if we're talking about y, because it's first order for y, it's not first order for z or for x. So I need to go back and look at my equation here, which is 2x plus y makes z. So let me write this down here. So 2x plus y makes z. And let's think about what's happening here. In order from z to go from 0 to 0.2, that means that we made 0.2 moles of z. And looking at my mole ratios here, in order to make 0.2 moles of z, I must have used up 0.2 moles of y, because they react in a 1-to-1 ratio. Every z you make must use up a y. And if I used up 0.2 moles of y, if my y started at 0.6, at the end, it's going to be 0.6 minus 0.2. It is now 0.4 molar. And you might be wondering why I'm using a mole ratio, but the units here are molarity. Remember, molarity is a measure of moles, because it's the moles per liter. So you can use mole ratios when you're talking about molarities here, if that makes sense. We're assuming the volume stays the same. So every 0.2 moles that get used up, your molarity is going to decrease by 0.2. Okay, so now I've got some info I can work with. I'm trying to solve for time. I know k. I know the initial value of y. I know the final value of y. So I can plug these into my integrated rate law, which is right up here. It's a first order integrated rate law. We know that because we figured out the reaction order in, parts A and B. So I'm just going to start plugging numbers in. So the natural log of y at time t, that is 0.4, minus the natural log of y at time 0, that's 0.6, equals negative 0.007 s minus 1 times t. T is my unknown. So when I go through and solve for this, I didn't write down what the actual numbers are, but you end up with t being 58 seconds. So the natural log, these end up being unitless numbers. Remember, be careful about your negative signs, and you end up with a unitless number divided by the inverse of the seconds, so the answer is going to be in seconds. All right, thanks for watching.